Okay, now this mean value theorem has very important and significant applications. Like I said, mean value theorem itself is an application or corollary of Rolle's theorem, but now mean value theorem itself has many applications. So let me start with an example, and then I will tell you about the applications. Okay, so example, let f of x equals, let's say, 2x cubed plus x squared minus x plus 1 on the interval, let's say, -1 to 3. Show that the conditions of mean value theorem. Mean value theorem, by the way, normally it's abbreviated by MVT in mathematics. When you say MVT, also in Math 114, if your instructor talks about MVT, it means mean value theorem. So the conditions of MVT or mean value theorem hold, and find the value or values of C. Okay. So what are the conditions of mean value theorem? The function has to be continuous on the closed interval, differentiable on the open interval. That's all. For Rolle's theorem, it was this condition plus f of a equals f of b, but we don't need f of a equals f of b for mean value theorem. Okay, so for both these theorems that we did today, you need the continuity on the closed interval, differentiability on the open interval. For Rolle's theorem, you also need f of a equals f of b. For mean value theorem, no. Just continuity on the closed interval, differentiability on the open interval. So here's a solution. F of x is a polynomial. So it's differentiable and continuous everywhere. So that's it. So the conditions hold. Conditions of MVT hold. Now, therefore, MVT implies or guarantees existence of a value of existence of a C value with f prime of C equals f of B minus f of A over B minus A. Let's find C. So MVT guarantees existence of such a C value. Now we want to find this C value. So f prime of C has to be equal to f of B minus f of A over B minus A. Now A is -1, B is 3. So f of 3 minus f of -1 over 3 minus -1. And then this is 2 times 3 cubed. How much is f of 3? 2 times 3 cubed. Plus 3 squared minus 3 plus 1. Minus f of -1, which is 2 times -1 cubed plus -1 squared, and minus -1 plus 1. and then the whole divided by 4. 3 minus 1 is 4. And then this is 27 times 2, 54, plus 9 minus 2 minus, so this one inside the bracket is minus 2 plus 1 plus 1 plus 1, so plus 3. 3 minus 2 is 1, divided by 4, and the answer will be 63 minus 3, 60 over 4, which is 15. Okay, so we have to solve for f prime of c equals 15. Okay, now what is the expression for f prime of c? Let's find f prime of x. So here, f prime of x is, we just need to differentiate f of x, derivative of this function, 6x squared plus 2x minus 1. 6x squared minus 2x minus 1. Say plus 2x minus 1. So it's f prime of c equals 15, means 6c squared plus 2c minus 1 equals 15. And that means 6c squared minus 2c minus 16 equals 0. If I divide everything by 2, 3c squared minus c minus 8 equals 0. So c is equal to 1 plus minus root 1 plus 4 times 3 times 8 divided by 6. And then this is 1 plus minus root. So this is 12 times 8, which is 96, plus 1 is 97, divided by 6. So we have two values for c. C equals 1 plus root 97 divided by 6. And c equals 1 minus root 97 divided by 6. Now we have to see which of these c values lie inside our interval, because remember, c has to be inside the interval that is given. What is the interval that's given? -1 to 3. So we will only accept the c values inside this interval and reject any c value outside this interval. So only accept values of c in -1 to 3. So root 97 is 9 point something plus 1 is 10 point something divided by 6 is less than 2. So it is in the interval, in this interval. So c equals 1 plus root 97 over 6 is inside the interval -1 to 3. So that's okay. What about 1 minus this? 1 minus 9 point something means -8 point something divided by 6 will be less than -1. So c equals 1 minus root 97 divided by 6 is less than -1. So not in -1 to 3. So we have only one value of c. Which is this c value. Okay. So now I want to ask a question here. So before I haven't started the applications yet, but just let me ask you one question. See, in all the examples we have seen so far, we had one value for c, whether for Rolle's theorem or mean value theorem. We had a function on an interval. We had one value for c. But do you think that's always the case, or we can have more than one value for c? So is C as stated in mean value theorem unique? The answer is not necessarily. Let me give you an example where it shows that you can have more than one C value. Let's say f of x equals sine x. Let's say on 0 to 4 pi. Find C values as stated by MVT. So first of all, MVT, we can apply MVT for f of x, because f of x is a trigonometric function sine x, basically sine x. We know that sine x is continuous and differentiable everywhere. So no solution. F of x equals sine x is differentiable and continuous everywhere. So we can apply MVT. And what do we want to solve? We want to solve f prime of C equals f of B, which is f of 4 pi minus f of 0 over 4 pi minus 0. The interval was 0 to 4 pi. And sine 0, of course, is 0. Sine 4 pi is also 0. So this is 0 minus 0 over 4 pi, which is 0. And what is f prime of C? Well, f prime of x, derivative of sine x is cos x. So cos C equals 0. And we want the solutions in which interval? In the interval 0 to 4 pi. What are the solutions for cos C equals 0 in the interval 0 to 4 pi? So C1 equals, the first solution is pi half. Then C2, 3 pi half. C3, 5 pi half. And C4, 7 pi half. So 4 values for C, 4 values for C. So we showed that we can have more than one value for C depending on the function. So in the previous cases, we had one value for C, but for this function, we have 4 values of C. You could define another function with 2 values of C or anything. So when the theorem says there exists a value of C with this property, it doesn't mean there exists one value. It means there exists at least one value. It could be more. But if there is another theorem where in another topic, let's say where it says there exists a unique value for C with such property, then that means exactly one value of C will exist. But here, and no mentioning of uniqueness. There's no mentioning of uniqueness, so we can have more than one value for C. Okay, now let's look at some applications of MVT. Let me start with an application in physics. So first application in physics. Let me show you in an example how we can apply MVT in physics and interpret about the velocity of an object. So you are driving, suppose that you're driving on a straight highway. And the speed limit is 55 miles per hour at 8:05. A police car clocks your velocity at 50 miles per hour and at 8:10 a second police car posted 5 miles down the road, clocks your velocity at 55 miles per hour. Explain why. The police have a right to charge you with a speeding violation. Speeding violation. Okay, so here we have a function. Basically, our function is x of t, the position. So here, our function x of t defined on the interval, defined, let me say, defined between 8:05 and 8:10 a.m. Okay, so normally in mathematics, you have f of x. X is an independent variable and y is a dependent variable. But in physics, usually you have x of t. So t is independent variable, x is the dependent variable. So we have x of t defined between 8:05 and 8:10 because it says at 8:05 the velocity is registered as 50 and at 8:10 registered at 55. Now, if I set t equals 0, because normally in physics we know we need a t equals 0 at some specific time. So there is no mentioning of any time before 8:05. So why don't I set t equals 0 to be 8:05? So set t equals 0 at 8:05 a.m. Then at 8:10, t will be how much? Because we want everything in hours. So let me write in hour. It will be 1/12, right? 5 minutes means 1/12 hours at 8:10. So this is T1 and this is T2. Okay, so by mean value theorem, we can say that there exists a C value between 0 to 1/12 such that x prime of C equals what? X of T2 minus x of t1 divided by t2 minus t1, or in other words, delta x over delta t, or the average velocity. How can I find average velocity? Delta x over delta t. How much the car moves in the time delta t in 5 minutes, or 1 over 12 hours? It moves 5 miles. See, when you read the question, it says second police car posted 5 miles down the road. So delta x is 5 miles. And delta t is, we said, 1 over 12 hours. So that's 60 miles per hour. So x prime of c, so for at least one c value between 0 and 1 over 12, which means between 805 and 810, for at least one particular moment, x prime of c becomes 60. X prime of c means what? Means v of c. Derivative of x is velocity, right? So we know that v of t, x prime of t is v of t. X prime of t equals v of t. So that means v of c is equal to 60 miles per hour for at least one value of c in 0 to 1 over 12. So what does that mean? That means v of c means velocity of the car. So at least at one moment between 8:05 a.m. and 8:10 a.m., the velocity of the car must have been 60 miles per hour. So that means the police has the right to charge with speeding violation. Because remember, the speed limit in this highway was 55 miles per hour, but at least in one moment, the car must have had the velocity of 60 miles per hour. So the police has the right to charge with speeding violation. All right, so this was the first application. Now let's look at the next application, second application. Constant difference theorem. Constant difference theorem. So let me remind you that previously we have seen, when we were doing derivative rules, we saw that if we have a constant function, then the derivative of that function must be 0. So we have saw before that if, let's say, f of x equals c, a constant function, defined on some interval, let's say a to b, then f prime of x equals 0 for every x between a to b. So derivative of in other words, the derivative of a constant function is 0. Now I want to ask about the converse of this statement. So what about the converse? Now the question is, is the converse true? Meaning that if the derivative of a function is 0, is identically 0, is identically 0 on some interval a to b, then can we conclude, then can we say that f of x is a constant function on that interval This is most of the times confusing for students because many students do not think about or do not realize about the difference between a statement and the converse of a statement. In mathematics, if a statement, or in logic in general, if a statement is true, the converse of it may or may not be true. So for example, I say if it's a Monday, then I go to the college. Let's assume this is true. Let's say I go to college, for example, let's say on Mondays and Thursdays. And therefore, let's say if it's a Monday, then I go to the college. So this is true. But what about the converse? Converse means change the assumption with the statement. The converse reads as, if I go to the college, then it must be a Monday. Now, this statement, this converse is obviously not true because, of course, it's possible that it's a Thursday. I go to college and because I assume that I go to college on Mondays and Thursdays. So if I go to college, of course, it's possible that it's a Thursday and not a Monday. So we cannot conclude that it must be a Monday if I go to the college. So I want you to notice that, there is always a difference between a statement and the converse of a statement in mathematics, okay? So one way here, one direction is obvious, almost obvious, using the derivative rules. It becomes obvious that if a function is a constant function, then the derivative must be 0. But what about the converse? If the derivative is 0, can I conclude that the function must be a constant function? Well, it's not obvious, but it is true, but it's not obvious. It's true based on mean value theorem. I will tell you the proof using the mean value theorem, but it's not obvious. So what is important here is that it's for you to know that if a function is constant function, then derivative is 0. That's almost obvious. If you accept the derivative rule, then it's obvious. But the converse of this is still true, but not obvious. And needs a proof, needs a separate proof. You cannot say that because the converse of it is obvious and it's true, so this is also true. We cannot say that because I just gave you examples that for some statements, the statement is true, but the converse is not true. How do we know this is not one of them? In other words, how do we know that if a derivative of a function is 0, well, potentially it's possible that there is a, let's say, weird function, let's say, for example, x times e to power x squared divided by root sine x, for example, plus something that, when you differentiate that function becomes identically 0. And that function is not a constant function. So potentially it's possible that the derivative of a function is 0, but that function is not necessarily a constant function. Potentially it's possible, but this theorem says that it's not actually possible based on the mean value theorem, but potentially it's possible. But the theorem says, no, there is no such possibility. Okay, so the theorem here is theorem. Let f of x be a continuous function on the closed interval a to b and differentiable on the open interval a to b. And suppose that f prime of x equals 0 for every x between a to b. Then f of x equals c, a constant function for every x in closed interval a to b. So if the derivative is 0 on the open interval and the function is continuous on the closed interval, then the function will be a constant function on the closed interval. Now let's prove this theorem. So we will show that f of x equals f of a for every x between a to b on the closed interval a to b. It's enough if I show this, right? Because see, I wanted to show that f of x equals some c for every x between a to b. Now, f of a is a constant. C means it must be a constant. F of a is a constant. So if I show that f of x equals f of a for every x between a to b, then I'm done, because f of a is a constant. I wanted to show that f of x equals a constant for every x between a to b. So case 1, if x equals a, then obviously f of x equals f of a. This is obvious, right? If x is a, then f of x is f of a, because x is a. This is obvious. Case 2, if x is not a, then that means x must be belong to open interval a to closed interval b. Since my screen is freezed.
Here is Farmer Tom. He pulls on his wellies ready for work. And here is Midge the dog. She's very cheeky.
Let me stop share. Share again. Okay, then I want to consider, then apply MVT for f of x on the interval, because here I am mentioning f of x. Let me call this one a t, maybe. You can call it t. For f of x on the interval a to t. See, t here is strictly bigger than a, because if t equals a, then we have covered that in case 1. In case 2, we are assuming t is strictly bigger than a. So I can consider the interval a to t and apply MVT for f of x between a to t. Note that f of x is continuous on a to t and differentiable on a to t, right? So the conditions of MVT hold, because I'm assuming that f of x is continuous on a to b and differentiable on a to b. So of course, and t is between a to b. Let me show you. See, and if this is the x-axis, this is, let's say, a, this is b, t is somewhere here. So if f of x is continuous differentiable on the whole a to b, of course, will be continuous differentiable between a to t as well. Okay. So So we can apply MVT between A to T. Then what can we say? So we can say there exists, thus by MVT, there exists C between A to T such that F prime of C is equal to F of T minus F of A over T minus A. But by assumption, what do we know about F prime of C? Look at the assumption of the theorem. Each theorem has some assumptions. You have to use those assumptions in order to prove the conclusion or the statement. My assumption is that F prime of X equals 0 for every X between A to B. Now look at C. Where is C? C is some point between A to T. So in particular, it's between A to B. T itself is between A to B and C is between A to T. So C, of course, is between A to B as well. And I'm assuming that F prime of X is 0 for every X between A to B. So F prime of C is also 0. So by assumption, we can say that F prime of C equals 0. And that means F of T minus F of A over T minus A equals 0. And now if a fraction is 0, that means top has to be 0, numerator has to be 0. So that means F of T minus F of A equals 0. And that means F of T equals F of A as desired. So what did we show? We showed that F of T equals F of A for every T between A to B, which means the function is a constant function. F of X equals C for every C between F of X equals C for every X between A to B. Now, what is C? C is F of A. I found the constant actually. I want to show that the function is a constant function on the whole interval. Not only I showed that, I also found my constant. I showed that F of X is must be equal to F of A. First output for every X, not only of course for A, but also for every X between A to B. So the function is a constant function. So let's look at an example. Show that sine inverse X plus cos inverse X is equal to pi half for every X between -1 to 1. So this is a trigonometric identity. You saw a proof for this identity without calculus in pre-calculus, without derivatives, without using derivatives in high school and pre-calculus. Okay. So you saw one proof in Math 100. Now we want to do another proof, this time using derivatives. How can I use derivatives to show that this function sine inverse X plus cos inverse X equals pi half for every X between -1 to 1? So see, if you look at the theorem we just saw, we saw that if we have a function with derivative 0, then we can say that the function, it must be a constant function. Well, here we want to show that this function here, if I call it F of X, is equal to this constant, is a constant function, and the constant is supposed to be pi half for every X between -1 to 1. So why don't I call this left-hand side? Let's call it F of X. And let's see whether F prime of X is 0. If F prime of X is 0 for every, not just for one X, for every X in this open interval, then we can say that the function must be a constant function. So let the solution let F of X equals sine inverse X plus cos inverse X. Then F of X is, first of all, continuous on minus 1 to 1, and f of x is differentiable on minus 1 to 1. Property of inverse trig functions. And also f prime of x is equal to what? What is derivative of this function? Derivative of sine inverse x is 1 over root 1 minus x squared. Derivative of cos inverse is minus 1 over root 1 minus x squared, which is 0 for every x in the open interval minus 1 to 1. So by theorem above, f of x equals c f of x equals c for a constant c and for every x between minus 1 to 1. So then if the conditions of the theorem we just proved hold, meaning that if the function is differentiable on the open interval, continuous on the closed interval, and f prime is 0 on the open interval, then f of x must be a constant function, meaning that f of x must be equal to some constant c for every x on the closed interval. Now it just remains to find the constant c. We know that f of x is a constant function, but what is the constant? We just need to find the constant. So to find the constant, plug in any value of x of your choice. Because f of x is equal to some constant c for every x, right? So I just need to choose one value of x and plug it here, and then that should be my constant. Then f of x will be equal to the same constant for every x. Because all of f of x values are equal to the same constant. So if I find one of the f of x values, then every f of x value must be equal to the same constant. So choose any x value between minus 1 to 1, and then find f of x, and then you will find your constant that way. And let me choose, let's say c or x equals 0. Let's choose x equals 0. Then we get a sine inverse 0 plus cos inverse 0, which is my f of 0 equals c. And that means c equals pi half, because sine inverse 0 is 0, cos inverse 0 is pi half. So then we can say that f of x equals sine inverse x plus cos inverse x equals pi half for every x between minus 1 to 1. All right, now a conclusion of this theorem is a theorem called constant difference theorem that I mentioned earlier, that we are going to cover this constant difference theorem. So in the previous theorem, I had one function f of x, and derivative of that function was 0. Now in constant difference theorem, I have two functions, f of x and g of x, and derivative of f is equal to derivative of g. So suppose that f of x and g of x are two functions that are continuous on a to b and differentiable on a to b, and suppose that f prime of x equals g prime of x for every x between a to b then we can say that f of x equals g of x plus c for some constant c, and for every x between a to b. So if you have two functions this time and derivative of those two functions are equal for every x between a to b, then one of those functions is equal to the other one plus some constant. So graphically, if I want to explain this, so when you say f of x is g of x plus c, that means one function is same as the other function plus some constant c, which means a vertical shift, right? So if you add one function with another, let's say we have x squared, and let's say you add it with one, x squared plus one. X squared plus one is a vertical shift, can be obtained with by a vertical shift of x squared. Or any other function, sine x and sine x plus one. Sine x plus one can be obtained by a vertical shift of sine x. So if I have a g of x here, let's say if this is my g of x, then f of x must be, if the derivative of f and g are always equal, then f of x must be a vertical shift of g, and then this shift, amount of this shift is c. So I can say, in other words, the graph of f of x must be a vertical shift of the graph of g of x. Okay. All right, let me prove this theorem now. Proof of this theorem called constant difference theorem. So I want to apply the previous theorem. In the previous theorem, we had a function, one function whose derivative was 0. Let me show you. We had one function f whose derivative was 0, and then we could say that that function must be called a constant function. Here we have two functions and the derivatives are not 0 necessarily. So how can I relate it to the previous theorem? So always in mathematics, one goal is to try to connect if we want to prove a result, we want to always try to connect it to the previous results or theorems. So how can I connect it to that theorem? I can define one function whose derivative is 0 and then apply that theorem, previous theorem. Well, what function should I define? Let's say if I want to, because f and g are already used, let me call the new function that I want to define h. How should I define h so that derivative of h becomes 0? Well, f prime is equal to g prime according to my assumption, right? So f prime equals g prime means f prime minus g prime equals 0. So I have to define h, the new function, as f minus g, and then I can say that h prime becomes 0. So proof, set h of x as f of x minus g of x, again on the same interval that f and g are defined, which we called it a and b. Then h of x is continuous on a and b, close interval a and b, since f and g are continuous. are assumed to be continuous. And also h of x is differentiable on a to b. Again, since f and g are assumed to be differentiable, right? We know that the difference, the subtraction or the addition of two continuous functions is continuous, and subtraction or addition of two differentiable functions is also continuous. Moreover, h prime of x is equal to f prime of x minus g prime of x according to the derivative rules. And f prime minus g prime is equal to 0 because according to my assumption, f prime is equal to g prime. So f prime minus g prime equals 0. So by previous theorem, we can conclude that there exists a constant c such that h of x is equal to c for every x between a to b. But what is h of x? H of x, we defined it as f of x minus g of x. So that means f of x minus g of x equals c for every x in a to b. And that means f of x is equal to g of x plus c, again for every x between a to b. That's what we wanted to show. That one function is same as the other one plus some constant c for every x between a to b. Now let's look at an example of this theorem. Find all functions f of x, find all functions f such that f prime of x is equal to 2x. You want to find the list of all functions whose derivatives are 2x. So in Math 114, you will write this question as finding antiderivative of 2x. When you say you want to find a function whose derivative is 2x, that means you want to find the antiderivative of 2x. Antiderivative of 2x means a function f whose derivative is 2x. So that's one of the main goals in Math 114. In Math 114, next semester, one of your main goals will be finding antiderivative of a given function. Okay, so what do we know as solution? We know that the derivative of 2x squared, we know that derivative of x squared is 2x, so that's what we know for sure, right? Derivative of x squared is 2x. Now, so we want to find all functions f whose derivatives are same as derivative of x squared. So we are looking for all functions f such that d to dx of f of x is equal to d to dx of x squared. This is exactly the setting that we had in the constant difference theorem. Constant difference theorem said if derivative of two functions are always equal for every x, then those two functions are equal themselves up to a constant, meaning that one of them could be equal to the other one plus some constant possibly. So this is true for every x. So by constant difference theorem, we can say that f of x is equal to the other function, which is x squared plus some constant c, for some constant c. So what did we show then? So we showed that any antiderivative, so this is a solution. We wanted to find all functions f whose derivatives are 2x. So the list of all such functions will be any function of the form x squared plus c for some constant c. So we showed that any antiderivative of 2x is of the form x squared plus c for some constant c. So you will use this fact frequently in Math 140. Another name for antiderivative is indefinite integral. So indefinite integral of 2x is x squared plus c. Why is x squared plus c? Next semester, remember today that we showed that once you have the derivative of a function, if derivative of another function equals derivative of the first function, then those two functions must be equal up to a constant, meaning that one of them is same as the other one plus some constant c. So 2x is derivative of x squared. So if you want derivative of some function f to be 2x, that means you want derivative of f to be same as derivative of x squared. And constant difference theorem implies that those two functions must be equal up to a constant, meaning that f of x must be equal to x squared plus some constant c. So any antiderivative of 2x is of the form x squared plus c. So similarly, you can show that any antiderivative of, for example, 3x squared is of the form x cubed plus c. Or antiderivative of cos x is sine x plus c, and so on. And like I said, in Math 114, you will call this antiderivative, and another name you will see it's indefinite integral. Okay, so you can see that why this mean value theorem is very important, because it had a significant important application called constant difference theorem, and constant difference theorem itself helped us to find all antiderivatives of a given function and the form of an arbitrary antiderivative for a given function, the general form. Okay, so another application for mean value theorem is proving inequalities. This is another application. So suppose that f of x is a function, is a differentiable function. And suppose that we want to bound this quantity, let's say f of x minus f of y over x minus y for some x and y in the domain of f . So say we want to show, that, let's say, this quantity f of x minus f of y over x minus y in absolute value, let's say, is equal less than equal to some m for some constant m. Now f of x minus f of y over x minus y, if f is differentiable according to mean value theorem, is equal to what? Do you remember the statement of mean value theorem? It was saying that let me show you the statement here. F of b minus f of a over b minus a is equal to f prime of c for some c between a and b. Okay, and this is exactly the setting that we have here, f of x minus f of y over x minus y. So this is equal to f prime of c for some constant c between x to y. So by MVT, f of x minus f of y over x minus y equals f prime of c for some c between x and y. So it is enough to show absolute value f prime of x is less than equal to m for every x in domain of f, right? If you show this, let's assume you show this in some way. Let's assume this is easy to prove, that the absolute value f prime of x for every x in domain is less than m. Well, this implies that absolute value f prime of c is less than m, because if this is true for every x, it will be true for c in particular as well, right? Because c is some number between x and y, therefore some number in the domain. So if this is true for every x in domain, it will be true for c as well. And if absolute value f prime of c is less than m, well, f prime of c is equal to this expression. So that means this expression in absolute value less than m, which is what we wanted to show. Okay, so this is how we can apply MVT to prove some inequalities. Not all inequalities in the world, of course, but some of the important inequalities in mathematics and in calculus can be proved using this technique. So let's look at an example. Show that absolute value sine x minus sine y is less than equal to absolute value x minus y for every x and y in R. Okay, solution. For solution, I want to consider two cases. Case one, if x equals y, if these two numbers, because it says for every x and y in R, it doesn't say x must be equal to y or not equal to y. So let's first assume the case where x equals y. Then how much will be the left-hand side? Then the left-hand side will be absolute value sine x minus sine x, which is 0. Right-hand side will be absolute value x minus x, that's also 0. And therefore absolute value sine x minus sine y will be less than equal to absolute value x minus y. So we have no problem in this case. Okay, the screen is freezed. Okay. So no problem in this case, because in this case, if x equals y, this left-hand side and right-hand side of these inequalities will be both equal to 0. And of course, 0 is less than equal to 0. So no problem. Now, case 2, if x not equal to y, and then I want to say that, then we can say, then absolute value sine x minus sine y less than equal to absolute value x minus y will be equivalent with absolute value sine x minus sine y divided by absolute value x minus y less than equal to 1. Because remember, absolute value x minus y will be positive in this case. See, absolute value x minus absolute value of any number is always bigger than equal to 0. But if I want to divide by this number, it's not allowed to be 0. But if x not equal to y, which is what I'm assuming in case 2, x minus y will be not 0. So in absolute value will be not 0 either. And therefore, it will be positive because remember that absolute value x minus y must be bigger than or equal to 0. And if it's not equal to 0, then it must be bigger than 0. So absolute value x minus y will be bigger than 0. And of course, if I have an inequality, I'm allowed to divide both sides of the inequality by a positive number. And the inequality remains in the same direction. If that number was negative, then the inequality would flip. But because right now I have a guarantee that this number is positive, absolute value x minus y, so the inequality remains in the same direction. So absolute value sine x minus sine y over absolute value x minus y will be less than or equal to 1. So this is equivalent with this. If you want to go from this to this, you have to divide by this number. If you want to go from this to this, you have to multiply by this number. So anyways, these two expressions are equivalent with each other, meaning that instead of proving this, I can just simply prove this. And this expression itself is equivalent with absolute value sine x minus sine y over x minus y less than or equal to 1. Okay. So now see, this is an expression that I was talking about, f of x minus f of y over x minus y. So now set f of x equals sine x, which is differentiable and continuous everywhere. So by MVT, we can say that f of x minus f of y over x minus y equals sine x minus sine y over x minus y equals f prime of c for some c between x and y. But what is f prime of c? F of x is sine x. So that means sine f prime of x means is cos x, right? F of x is sine x, so f prime of x is cos x. So I can say sine x minus sine y divided by x minus y is equal to cos c. Again, like I said, for some c between x and y. So absolute value sine x minus sine y divided by x minus y will be equal to absolute value cos c, which is less than or equal to 1, right? Absolute value cos of any number in the world is always less than or equal to 1. So this is a property you saw in math 100 or 110 or pre-calculus or high school, that absolute value cos of any number is less than or equal to 1, because cos of any number in the world is between -1 to 1, and therefore in absolute value cos of any number in the world will be less than or equal to 1. So what did we show? So we showed that so here I can say cos theta in absolute value is less than or equal to 1 for every theta. So we showed that absolute value sine x minus sine y over x minus y less than or equal to 1. And this means that absolute, if I multiply both sides with absolute value x minus y, which is a positive quantity in this case, that means absolute value sine x minus sine y less than equal to absolute value x minus y. So that's it. So this was the end of proof for case 2, where x is not equal to y. We still prove that the inequality that we wanted to show. Basically, this inequality here still holds, whether x is equal to y or x is not equal to y. Okay, so I will try to include more examples and exercises from inequalities in the assignments, and also other applications and examples of mean value theorem and Rolle's theorem. Okay, guys, so thank you and see you next time.